Hello, welcome to lecture 19. We're in JIAM section 3.6 today, which is about proving existential statements. Uh, the, the layout today is going to look more or less like this. First, I'll make a few comments about the philosophy of what we're doing in this section, then some quick examples, and then we'll look into some particularly interesting things, the well-ordering principle, I'd say, and a couple of questions about unique existence. Along the way, there's one sort of just for fun computer experiment we're going to run. Okay, so the philosophy here, the issue is that since proving an existential statement is the same thing as disproving a universal statement, we've already had a section that was about disproving universal statements, so we're kind of repeating ourselves, aren't we? Also, if you're thinking about disproving an existential statement, that's the same thing as proving a corresponding universal statement. So again, it feels repetitious. It seems like we could just not do this section, but here's the point. There are actually some times when more emphasis is placed on the existence question. And so it makes a certain sense to handle this. And also, it's sort of part of the culture. There are certain should I say memes? There are certain general techniques that people use again and again when they're proving things about existentials. So it's good for you to kind of know those ropes. Why do I mention Missouri and their state motto, the "Show Me State"? Well, that's maybe a little lame, but that is exactly what you do to prove an existential statement. Show me an example that will irrefutably prove that the thing exists if you can show me one. Let's do some trivial examples, some quickies, as they say. There is an even prime. Yeah, I can just pick up two and show it to you and say, yep, there it is. It's an even and it's prime. There is a Fibonacci number that is a perfect square. Okay, maybe a little tougher. I think I might want to do some scrap work on this. Oh, I could probably do it on the calculator. That'd be clever. So Fibonacci numbers work like this. You start with a couple of ones, and you always get the next Fibonacci number by adding the last two. So 1 and 1 is 2, and then we would have 1 plus 2 to get the one after that. That's 3. And then 2 plus 3 would be the one after that. 5. 3 plus 5 is 8. I'm not seeing any squares. I hope they're not misleading us here. 5 plus 8. Nope, hit the wrong button. 8 is 13, still not good. 8 plus 13, 21. 13 plus 21, 34. Geez, I wonder how long I got to go. 21 plus 34, 55. Are you sure there's a perfect square amongst the Fibonacci numbers? I'm starting to run out of steam here. All right, let me just go a little farther. 55 plus 34 is 89. That's not a square. 89 plus 55. The ooh, I recognize that one. 144 is a square. Actually, I kind of knew that already because it's the famous punchline to the Fibonacci story. This thing about breeding pairs of rabbits. So after 12 months of rabbits incestuously breeding with one another, you end up with 144 pairs of rabbits. Did you notice that this was a not trying, but it definitely required a calculator. The actual origin of the problem is as an exercise for people learning to use an abacus. So, and it sort of makes sense there that if you have to keep hold of a running total and also do some addition problems along the way, it's a little bit extra skill at using an abacus, which I don't know, that's kind of cool. Anyway, yes, there is. 144 is a Fibonacci number because we got it from this bit about adding up the previous two. And it's also clearly a perfect square. It's 12 squared. There is a magic number. Okay, so the magic number trick is a great I don't know. I guess I'd call it a puzzle, but it's sort of a shtick that you can play with people who haven't heard it before. and it mystifies them entirely. Um, I'll tell you, the actual answer is 4 is the magic number. That's what the magic number is. But what you do is ask them to give you a number. They give you a number, and you then go through a routine like this. Suppose you gave me the number 11. I would say 11 is 6, and 6 is 3, and 3 is 5, and 5 is 4, and 4 is the magic number. And no matter what number somebody gives you, you can always do some string of computations until you come back to 4. Why is 4 the magic number? It's because the computation you're doing is just counting how many letters are in the word. Spell out the number, count up how many letters are in it, and then that's the next thing. So usually what I get busted on this because at some point somebody asks me to do like 38 and I have to sit there on my fingers and count up the letters in 38 and so then they guess. Or maybe I'm just being clever and I want them to guess because this takes forever so yeah, anyway, that's the magic number 4. Exciting. Well, we had 4 fours last time, so another mystical occurrence of 4. All right, some more actual examples of proofs that aren't just quickies like that. What often we have there are standard tools that will create existence things for us. The intermediate value theorem is something from calculus that does that. What the theorem says is that, and watch out, the hypothesis needs to be valid, that you have a continuous function. If you have a continuous function that's defined on some interval, a to b, then for any real number that lies between your value at a and your value at b, that's what I'm saying right here. There's a real number r that any real number r that lies between f of a and f of b. Well, you can find some x in that interval such that f of x equals to r for any real number. So how do you actually use that in practice? It goes a lot like this. You use it to find the existence of a root. Root is turning into a deprecated term these days. So if you've only heard zeros of a polynomial, that's what I'm talking about. If you have any function, though, you can find a zero of it. And using the intermediate value theorem, you can do what's known as right, it's called binary search. So you can zero in usually rather quickly on where the root is by this, but you use the IVT to make it happen. So you need to have a place where the function is positive and another place where it's negative. Could be f at a is positive, f at b is negative, or vice versa. But once you've got that, the intermediate value theorem guarantees there's somewhere in between where the function will be 0. So you can know that is in there. I'll give you a quick example of it. If we looked at the polynomial x cubed minus 2, of course, all polynomial functions are continuous, so we've got the hypothesis we need. At 1, you can just plug 1 into this and you get -2 as an answer. And at 2, if you plug 2 into here, 2 cubed minus 2 is 6. So one number is negative, the other number is positive. That means somewhere in between, that function has to go through 0, has to pass through the x-axis. So that means there is an x in the interval 1 to 2 where f of x is 0. What have we just done? Well, that function is actually chosen in order to find it's chosen to make sure that the solution to it being equal to 0 does something useful. It finds the cube root of 2. If you could take x cubed minus 7, you'd be able to locate the cube root of 7. And the cube root of 2 lies somewhere in between 1 and 2. Now, the search for the actual cube root of 2 might go something like this. We'll cut that interval in half, go to 1.5. Right? Play the same game again. Out of between 1 and 1.5, and then 1.5 and 2, one of those should have a plus and a minus entry. So we can use the one that has to trap the root in it to refine our estimate. Okay, well, that's if you take like numerical analysis, you'll get into doing that kind of stuff a lot. Here's another approach. This actually is sort of my favorite um, elementary proof in all of mathematics. It's kind of just it's mind-boggling, but um, simple. So, what do you think about this question? Do you think that if you took an irrational number and raised it to an irrational power, could it possibly be rational? I think it sounds crazy. Couldn't be, right? So, weirdly, it's actually true that, and I'm just rooting it into standard math notation. There exists alpha and beta in the reals, where alpha is not a rational number and beta is not a rational number, and alpha to the beta is a rational number. That's what that's saying. So, the weirdest thing, in my opinion, about this is we know it's true that there are alpha and beta, but we have no idea what they are. That's the only problem with this thing is it doesn't tell us what the things are, it just tells us they exist. So, let's see how this proof goes. Um, First, just ask, is root 2 raised to the root 2 a rational number? There's only two options, right? It either is or it isn't. I may not know which one it is, but I know that it's either one or the other. So that sets me up for dilemma. I can, if we were doing it formally, I'd say introduce the tautology. Root 2 to the root 2 is rational, or root 2 to the root 2 is irrational. One or the other. Well, anyway, if it's rational, we're done because you can let alpha and beta both be root 2. So you don't have to worry about that case. And if it's irrational, you're almost done. Let alpha be that number, root 2 to the root 2, and let beta be root 2. And let me just show you the computation that says, okay, that's going to work out. Alpha to the beta then looks like root 2 to the root 2 raised to the root 2. The way exponents work, though, that you can sort of bring this exponent onto the inside, it becomes a multiplication. So that's simplified to root 2 raised to the root 2 times root 2 power. But root 2 times root 2 is 2. Yeah, so you get root 2 raised to the 2, that's 2. That's clearly a rational number. So I don't know what the actual situation is. I know root 2 is irrational. I don't know whether this thing is irrational. Um, I think it likely that it is, but I definitely know that these two, when I raise this irrational to this irrational, I get a rational, which is messed up. And even if I wasn't more or less convinced that root 2 to the root 2 was uh, irrational, the answer would still be there. Then I could use alpha and beta being root 2. You see how the dilemma gets us an answer without us knowing what the true status of root 2 to root 2 is. All right, the well ordering principle. Uh, Here's what it says. A set is said to have the well ordering principle if every subset of it must have a least element. So when I first heard this, I thought that they had named it poorly, that it was somebody who maybe didn't really understand English grammar that well. Because well versus good, let's see, good is an adjective, well is a adverb. You do something well, something good might happen to you, right? Um, so why would we talk about an ordering being well? We should talk about an ordering being good. And the problem, I think, although it's possible I'm making too much stew out of one oyster here, but I think the well in that phrase actually refers to the kinds of things that you get when you dig a hole in the ground and water comes bubbling up. So a well that's poked into the ground has a bottom. And I believe that's what they were trying to get at in calling this the well ordering principle. They're saying there's there's something about the ordering that makes that is akin to having a bottom. So that's the idea that every subset has a least element. Just the same idea that every well has a bottom to it. There's no such thing as a bottomless hole. So the natural numbers has the well ordering property. The integers do not have the well ordering property. For instance, if you think about the set of even integers, that's a subset of z. Is there a least element in that? No. But if you pick any subset of the naturals, there will be a least element in it because, well, 0 is sort of down here catching everything. You can't get smaller than 0 in the naturals. So But that's actually, interestingly, not the entire issue, because the positive rationals don't have the well-ordering principle, the well-ordering property. Uh, um, but they are bounded below. Why do they not have WAP? Well, think about the rational numbers that are in the interval 0 to 1, just, a tiny fraction of all the rational numbers. But is there a least one in that collection? If there is, try naming it, because what I'm going to do immediately is say, oh, yeah, well, I'll take half of that. And you're going to quickly get something even smaller. So you can reason pretty quickly that you can't name a smallest element of that set. Okay, so the naturals do have the well-ordering property. Any subset of the naturals will automatically have a least element. Even if we can't currently say what the thing is, we know there is a least element. And, well, that's kind of impressive. Let me give you a funny example. Well, funny, funny is the wrong phrase. I should say an interesting example and a current one. It's not that long ago, in 2013, a gentleman named Yitang Zhang proved that there are infinitely many pairs of consecutive primes that differ by 70 million. You might think, well, okay, why is that a big deal? Well, previously, nobody had been able to come up with any number that was the difference between consecutive primes infinitely often. So to say that there is some number that worked infinitely often as the gap between primes was kind of a big deal. What he did here is say there is some. Well, what he did was say there's a number that works. 70 million will be will occur as the gap between primes infinitely often. But that tells us, together with well-ordering principle, that there's a smallest natural number that occurs infinitely often as the gap between consecutive primes. Because now we know the set of gaps has got an element in it. There's something that occurs infinitely often amongst the primes. So that was actually a huge, huge deal. He proved a thing called the bounded gaps conjecture by coming up with that number. You notice it's an existential type proof. So sometimes the emphasis is on the existence. Prior to that, there was no reason to think any finite number would work as the gap between primes infinitely often. So since his discovery, other people have come along and improved it. I believe he's worked with some of them. They've got the state of the art down to 246 is a number that occurs infinitely often among the primes. We still don't know if that's the least number that occurs among the primes, but that's a lot of progress. But I just want to take note that the work from 70 million down to 246, that seems like a lot. But the way bigger job is going from infinity down to 70 million. So the fact that Zhang cracked this thing with 70 million was a stroke of genius. The getting it down to 246 is a matter of refining something that's already there. And obviously there was some brilliant work done in getting there too, but I would still claim the initial thing is the bigger deal. We still don't know what the smallest gap that occurs infinitely often is. And this is related to the twin primes conjecture, because if that smallest number turns out to be 2, that is the twin prime conjecture. If you can say 2 occurs as the gap between consecutive primes infinitely often, that's twin primes. So the bounded gaps conjecture did have there was reason for Zhang to be studying this. By working on that, he made significant progress towards cracking one of the biggest open questions in number theory. So going from that to a purely, how should we put it, a recreational problem. This, I think this problem first came out around Halloween one year. So, the naming of things is a little bit inclined towards that idea that we're following up a Halloween theme. A vampire number is a 2n digit number, V, call it V because vampires, right? It factors, though, as V equals X times Y, and X and Y are both going to be n digit numbers. They call the things fangs. The numbers x and y are called the fangs of V. So you get the idea. There's two fangs, and the product of them makes the vampire. Um, the deal, though, is that the digits in V and the digits in x and y together have to be precisely the same. Counting if there's some repeated digits, that's fine, but the counting those repetitions. So, although you are allowed to reorder stuff, right? So the digits in V would be a reordering of the digits that appear in x and y. There is a trivial situation that happens where both fangs end in a zero. That really means you're just looking at a vampire number of instead of 2n, I guess it would be 2 times n minus 1, the earlier version, and throwing and padding it with zeros. So that does produce some sort of trivial cases. So the definition includes eliminating that. So in the book, it notes that 125,460 is the same as 204 times 615. It's already been verified. I was thinking about getting out the calculator and checking that. And that is a 6-digit vampire number because you can see the digits, let's see, 204, there's a 6, there's the 1, there's the 5. Yeah, that 204 and 615 are exactly the same as the digits that appear in here. In fact, this particular number has another factorization into two fangs that have the same digits, but it's enough to just see this one. So we know now that there is a 6-digit vampire number, and that tells us there absolutely is a smallest 6-digit vampire number. That's what the well-ordering principle does for us. Do we know what it is? No, we don't. Right? Let me reiterate this since I got ahead of the slides. The vampire numbers, this collection of 6-digit vampire numbers is non-empty. We've got at least one of them. So the well-ordering principle guarantees that there's a smallest 6-digit vampire number. What is it? And in fact, in the book, it tells you what it is and asks you to verify that. But let's just go ahead and discover it. But I definitely want to do this with the help of a computer. So we'll use CoCalc. Let me start up a new Sage worksheet. Get my keyboard to where I can type efficiently. One thing we're going to need to code is a function that sort of pulls the digit. I was going to say sucks the digits out of a number. That would be in keeping with the vampire theme. But I want to make a list out of the digits of a number. So let's do a definition of a function. Let's call it how about get digits. I'm a fan of using this kind of a style in naming things where you capitalize the initial letters of a word. They call it camel case. Because it makes it easier to read, but you don't have spaces, which can sometimes cause troubles with compilers. Get digits. Well, it's going to take some number, so let's just call that n. And what should the body of this function? Oh, darn it! I just hit. By force of habit, I hit Shift and Enter, and we don't really want to see the error message that I don't have. I have an empty function definition there. I wanted to hit just plain Enter, so we didn't execute anything. All right, so what am I going to do? Well, I'm going to return a list of the digits. So let's call L that list, and we'll start it out with just, it's empty. Okay? But that's initializing that as a data structure to hold our return value. Well, I'm gonna do a little looping. So I'm going to try this on n. As long as n is not 0, I'm going to keep doing the same thing to it. And here's the thing I'm going to do to it. I'm going to peel off the units digit of it, and that is just n% 10. Right? Take n mod 10, and that gets the unit digits of it. Well, let's call that something. Let's call it d for digits. D equals n% 10. Okay? First, I'm going to append that value d to my list L. So I'll say L dot append. That's one of the functions that comes with a list. So a list has, well, actually, I should probably show you this. L equals, make a list with a couple of things in it. Oops. Shift Enter. And then if you type the name of that list, a period, and hit Tab, it'll show you all the things that you can do with a list, all the functions that are integral to that particular data type. You can count how many things are in it, you can append to it, you can extend it, you can find the index of something. Oh, never mind. I don't want to get into all of those, but you saw one of them was append, right? So let's just kill off this. Think of that as scrap work. I want to just show you something and hide my previous error here. All right, so what we're going to append then is that digit D. Now, if I just did that, I would now have a digit. The units place of n would be D again the next time I went through. So I also need to change n at this point. What I'm going to do is take away the D that we just did. And that guarantees, by the way, that I've now created an n that has a 0 in the units place. Yeah? So let's divide it by 10. Dividing by 10, especially if you have a 0 in the units place, just moves everybody over. Right? If you didn't have a 0 in the units place, it would create something that had something to the right of the decimal point. So what I'm going to do now is replace n with this thing that I just calculated in terms of n. So n is equal to n minus that digit divided by 10. You see how that works? I've captured d as a digit, and then I've shifted n down so that d isn't there, and now I only have 5 digits or fewer. Okay, is that going to do the whole trick? Well, I think that does it. Let's see if it compiles. It liked that much. Let's see if it works. Let's try to run get digits on a 4-digit number. I don't think it did anything. Let me call it L equals get digits. Oh, I'm being so silly. You know what I did wrong in this function? I had it do some work, but I never had it return a value. That was a real beginner's sort of mistake. I'm kind of embarrassed, but oh well. Yeah, we needed to, after we're finished with that loop, we need to return L. Yeah. Now I don't really need to do that. We got the list 4, 3, 2, 1. They're not in increasing order. There turns out there's a function for lists that sorts them, but it does the work in place, so you have to be a little cautious about using it. All right, so we've got this function that will kind of pluck the digits out of a number for us. We'll certainly need to use that, but then we have to think about how would we like to work our way through all the possible vampire numbers. For instance, I could do a loop that goes from 0 to a million. Does a million get 6? Well, 0 to 999,999. Actually, if we wanted to have 6 digits, I shouldn't do that. I should loop from wherever 6 digits begins to wherever 6 digits ends. I guess it's 100,000 up to 999,999. But I think it's more efficient and quicker to loop through all the possible fangs. So the fangs are 3-digit numbers in this case, and that means we could do a loop for, let's call it fang 1 is A. For A in the range from 100 up to 999. That's what we'll run all of the first fang through. And I want to do a little programmer's trick here just for efficiency's sake, which is to run, we're going to have a nested loop, as they call this, where one loop runs inside the other one. And in this one, I would like B to start out wherever A is. So at first, B will be running pretty much through the same range that A is, but towards the end, it'll be doing many less, because when you have two numbers, these two fangs, you might as well say, well, let A be the smaller of the two and B is the bigger one. So I can say B in range from wherever A is up to 999. And that cuts the amount of things that we're looking at in half. All right, so what are we going to do inside of this pair of nested loops? Well, I need to see if the product of those numbers has the same digits in it as the two of them together have collectively. Um, well, let me get the product. How about we call it P for product? P equals A times B. Let's compute that. Um, I also want to have the digit lists for both of them. And it turns out I should probably get the digit list for A inside of the A loop, but outside of the B loop. We don't need to be doing this work over and over again. Just once is fine. We'll call it X is equal to the result of getting the digits out of A. Right? But inside of this loop, inside of the B, we're going to need to do something similar for the digits of B. So Y is equal to get the digits of B. All right. Now the product is A times B. That's good. We've got the digits. Now I want to check, do the digits of X and Y together give me the same result as the digits of P? And let's do this. I'm going to do this by naming some new things. So how about M? M is going to be the digits that are in the fangs. So the digits from A, the digits from B. That is just, um, it's really an interesting thing. You would say you can't add those things, they're lists, but this is known as polymorphism. If there's a reasonable way to interpret the operation of adding between two things that are lists, and there is, it just means glob the lists together, then they do what's called overriding the operator. So they've done that, and addition of lists is defined, and so you can set M equal to just the sum of the two lists. And then I also would like to sort it. Again, I showed you before how to get the help, or how to get the use tab completion to see what functions are available for a list. Sort is one of them, and what that does is in the particular list M, it sorts itself. It's like the list doing it to itself. So the list changes itself in order to do that. Okay, that's one thing. That's the sorted list of the digits that are in the fangs. I'm going to need the sorted list of the digits that are in the product. So we'll do a similar thing, but we'll call it N is equal to get the digits from the product, which I call P, right? And just like with M, we want to sort that so that I can compare these two things, right? So here's the comparison. If M and N are actually equal as lists, which just means that they have identical entries right on down the row, then I found a vampire number. So if M equals N, what will we do? Well, shout excitedly that we found a vampire number. I guess I'll do that by printing some stuff. I will print A, and I will print B, and I will print the product. Well, that should be enough. So I wonder if this is going to work on the first go. You never know when you're coding stuff. I think I've got it, so let's go. Oh, it's starting to spit out vampire numbers. Well, there's kind of a lot of them. You can see the way the slider thing on the side is still moving. There's still more being produced. I guess we're done now. We got to A is in the 900s and B also in the 900s. Now, I could sit here and go through this and find the least thing in it, but that feels pretty stupid. Let me make the computer work for us this way. I'm going to define something, I'll call it least. And least is going to be, I'm going to start it out with a number that's too big, 99999. All right, and if I find one of these vampire numbers, so if I'm in this situation where the two lists are equal, now I'm going to check if it's smaller than the least. So that's yet another if statement, isn't it? If um, the product is less than least, we'll just replace least with the new number. And so I'll have it keep track of what's the smallest thing it's found to date, and it's going to update that every time it finds a smaller one. And so when this loop is finished running, and it didn't take that long to go through these, is it about a million things? 1,000 times 1,000, yeah, that's about a million. Okay, 900 times 900, still it's kind of amazingly fast. So the variable least should hold our smallest vampire number when we're done running through this. I seem to remember that it didn't take that long for it to run through all these possibilities before. It's kind of fun to watch it go. We're in the 600s, 700s. Well, we're done. All right. So what's the value of least? I'm sorry, shift enter. 102510. Now, we could search for that, I suppose. Oh, let's search for it the smart way. If you just use the browser search, I thought that would have brought up the browser search, but what I did is hit Control F, and it brought up the search within Sage. So 102510 was the number, right? Didn't seem to do anything. I'm trying to figure out what happened there. Let's see if I can get the browser search by doing Control F here. No. That's very weird because I did the browser search before in this. Maybe I'll just use it here. Control F. Well, of course it's there. And it's in my search bar. There it is in the midst. That was harder than it should have been. 201 times 510 is 102510. You see how the digits in the 6-digit number are exactly the same as the digits in the 2 3-digit numbers. And I think that was a nice example of using a computer to explore a problem a little bit. And that is something I'm very conscious of trying to encourage in students. I think you really gain something if you get a little facility. You don't have to become an expert programmer, but get a little facility at being able to get into a program and write a simple loop that will help you search through a pile of things. That's good stuff. All right, so let's get back to our slides. That's not our slides. These are our slides. Okay. So we got through that vampire number thing. Last thing we're going to talk about is something called unique existence. And it happens fairly frequently that we want to not only show something exists, but that it's the only one. It's like, wow, I don't know if you guys would ever have heard of the movie Highlander, but there was this pretty good movie called, well, good if you like this sort of thing, movie called Highlander. And there was like the catchphrase was, there can be only one. It was supposed to be like these immortal dudes who were going down through, they could never die, and they were going down through history fighting each other. And when one of them died, his like life force went into the other ones. And I'm not actually recommending that film. I'm just saying it exists. Anyway, there can be only one is sort of the idea of unique existence. So how do we express that in more grown-up mathematical terms? We put after the quantifier, we put an exclamation point. It's not read as factorial or anything. It just tells you that you're looking at unique existence. So here's an example. For all n and d in the naturals, there is a unique q in n, and there's a unique r in n, such that n equals qd plus r, and the remainder is the size it's supposed to be. So we saw that before, didn't we? I don't know if I pointed out the exclamation points, what they were doing for us, but that's basically the definition of quotient and remainder from the quotient remainder theorem, and they are uniquely determined by n and d. Yes, a unique existence proof usually has two parts. One, show the thing exists. Just show existence by whatever means possible. If you can show the thing literally, that's great. Do a dilemma approach like I did in that thing about the rational or the irrational numbers whose exponent was rational. Anyway, show existence whatever way you can, and then you do a little sort of miniature proof by contradiction to say, look, if there were two things that satisfied this, some kind of issue would happen, and so there's only the one. Um, that's a mini proof by contradiction. One of the things is often the case. The well ordering principle gets you that the thing you're looking for exists, or there are things like what you're looking for, and so the least one is going to be there. Well, the least one is unique, isn't it? Because, and here's the mini proof by contradiction. Suppose I had two things that satisfied whatever condition we're talking about, and they were both the smallest. Wouldn't they both be equal to each other? So my supposition that there were two is really false. There's just the one. The GCD of two natural numbers is a unique thing. And what I want to do is show you what I think is a nice sort of geometric interpretation of the integer arithmetic here to let you think about the GCD in a different way. There's a set that's called the Z module. A Z module generated by a single number is just all the multiples of that number, so not so exciting. But if you've got a Z module generated by two numbers, it's all the things that are, well, if it was A and B, like it's given there, it's X times A plus Y times B. And X and Y go over the integers, and so you get quantities that are related to A and B. Multiples both of A and B. If you've taken linear algebra, that's what's known as a linear combination. Although in linear algebra, you would usually have real numbers as the scalars. This is just integers as the multiplying factors. So I'll show you an example of this, and we'll see that you can spot a couple of handy things in the Z module. So what this is, there's a lot of numbers on a page, I know, but at any integer coordinate point, I've written down literally x times 21 and y times 15. So you notice, for instance, at 1, 0, we're seeing the number 21. At 0, 1, we're seeing the number 15. At 1, 1, is 21 plus 15 really 36? Yeah, these were computer generated, so trust me on that. And you should notice this blue shading on here. The blue is where numbers are negative. There are some linear combinations of 21s and 15s that are negative. It's real easy to see that. For instance, when y is minus 1 and x is 0, then you'll get the expressions right down there. Negative 15 plus 0. Yeah, well, that's what I got, negative 15 right there. There's a line, really, this edge here between the blue and the white, which is the line where it divides it up between the positive and negative ones. Right? And it's not terribly hard to figure out where that line lies, because you see that 0, 0 is a place where certainly the linear combination 21 times 0 plus 15 times 0, that's going to give you 0. Isn't there other places out here where we should find a 0? It's not that hard to notice. If you had x 15 and y negative 21, for instance, that'd be 15 units out along the x-axis, 21 units down along the y-axis. It's way below my screen, but it's still a point where I'm going to get 0. So you can figure out the slope of this is basically the slope of this is determined by the two numbers. It's a negative 21 over 15. I think that actually reduces, doesn't it? 7 over 5, negative 7 over 5. Yeah. All right. What the other thing I want to show you is if you look along this line, you will see there's numbers that repeat. You'll see them over and again. Like here's a 3 right here. Here's another 3 down here. I got an 18 just above that 3. Just above this other 3, there's an 18. Wow, 39 to the right of it. That's the same pattern. Right? So if you kind of swoop in from the high side and come down towards this negative, this line that separates the positive from the negative ones, you should encounter the small things that are multiples of, that are linear combinations of 21 and 15. And the smallest thing that I see is that 3 right there. In general, it turns out this is this is just a fact. The Z module's smallest positive entry is the GCD of the numbers. Do you see that these numbers are both divisible by 3? And in fact, 3 is the largest number that divides both of them. So there's an example. This isn't proof, but this is an example of seeing that the smallest positive element of the Z module is the GCD of the things. The nice part of saying that is there's a collection of positive numbers, of positive natural numbers that occur in the Z module. So that's a set, positive natural numbers, that has the Well-Oring principle, which means I know there's a least element in this collection. As soon as I know that there's anything in it, that it's a non-empty collection, and for instance, we already looked at 15. So that's a number that's in it. It's positive. So it's a non-empty collection. You can see all these other ones too because we're looking at it. But if we didn't have it displayed in front of us, we wouldn't necessarily know they were there. But sure, there is some positive number in this Z module. And so there's a least positive number in the Z module. And like I said just a little while ago, if you're talking about looking for uniqueness, the least element in a set is a unique thing. So this very directly gets you to the idea of the GCD being unique. Maybe not that directly, but it gets you there quickly by showing you this other structure, which turns out to be a very handy thing to think about. The Z module is generated by two numbers is, well, you won't see it right away, but you will see that again in your lives. Trust me, it comes up nicely. And being able to visualize it is better than just thinking of it as abstractly as a set. All right, back to our slides. And oh no, we're done with our slides. So that's the end of our session today. I hope you enjoyed it. Next time we are beginning chapter 4, which is about set theory. So we'll find that we'll go through chapter 4 rather quickly because it is almost a repeat of what happened in logic. I still recommend reading the sections before you come to look at these videos. But, so take a look at 4.1. I think you'll see that there's a lot that's very similar to what happened in logic. We just have to kind of change the notation a little bit, but you feel the same structures are present. All right, so thanks for listening, and have a great rest of your day.